In this lesson, we want to review applications of linear equations. We're going to look at mixture word problems. So again, when we're working with applications of linear equations, we have a little 6-step procedure that we can use. So for solving a word problem, we have as our first step, we want to read the problem and determine the question, or again, questions to be answered. Then we want to assign a variable to represent the unknown. We're going to express other unknowns in terms of this variable. Then we're going to write an equation, okay, based on the scenario we're given. Then we're going to solve the equation. Then we want to write the answer in terms of the question, or again, questions being asked. Then lastly, we're going to check the answer using the words of the problem. This one right here, number 6, the last step is very important. You want to make sure your answer is reasonable. So of all the word problem types that we encounter in elementary algebra courses, usually mixture problems give students the most trouble, right? When you're in that section on applications of linear equations. The key to understanding mixture problems is understanding how to find the pure amount of a substance in a mixture. To accomplish this task, we can multiply the rate of concentration as a decimal by the amount of the solution, okay? This will give us the pure amount of a substance in a mixture. So let's look at a simple example. So a local bar serves Pebble beer, which is 9% alcohol. So I'm just going to highlight this because they gave us a percentage. So 9% alcohol. If one serving is 20 ounces, let me just highlight that. So it's 20 ounces. How much pure alcohol is in each serving? So obviously this is what we want to answer here. How much pure alcohol is in each serving? So all I need to do is take the amount of one serving, which is 20 ounces. Forget about the ounces part for a minute, just the number 20. And it's 9% alcohol, okay? So all I need to do is multiply the 20 by 9% as a decimal, which is 0.09. If I do that calculation, I'm going to get 1.8, okay? So what this tells me is that this Pebble beer here is going to be 1.8 ounces of pure alcohol. So let me erase this and I'll write a nice little sentence. And we'll say that Pebble beer has 1.8 ounces of pure alcohol per serving. Okay, so a very simple example, just something we need to understand how to find the pure amount of something in a mixture or substance. So in this case, we have a beer. It's 9% alcohol. We want to know the pure amount of alcohol in the full serving, which is 20 ounces. Again, we take the rate of concentration, which is 0.09 as a decimal. We multiply it by that serving, which is 20 ounces. And that tells us we have 1.8 ounces of pure alcohol in each serving. All right, let's look at a typical word problem now. So we have that Mary is throwing a party and wants to serve fruit punch, which is 22% pure fruit juice. She currently has 2 gallons of cherry smash fruit punch, which is 50% pure fruit juice. How many gallons of bubbleberry fruit juice, which is 14% pure fruit juice, must be added to create her desired fruit punch? So understand what we're trying to find here. We're trying to find out how many gallons of this bubbleberry fruit juice, which again is 14% pure fruit juice, that's got to be added to create her desired fruit punch. And again, her desired fruit punch is 22% pure fruit juice. Okay, that's what we want. So let's get a little idea of what's going on. She has these 2 fruit punches that she's mixing together. One is the cherry smash and the other is the bubbleberry. Okay, so you can see that little image here. So she's mixing them together to get this final mixture here. And the final mixture is going to be 22% pure fruit juice. Okay, so that's the goal. So let's let a variable like x be equal to the amount of the bubbleberry fruit punch in gallons. Okay, so that's the amount she's going to use in gallons. So we'll say the amount, let me kind of erase that. So we'll say the amount of the bubbleberry fruit punch used, and this is going to be in gallons. Okay, in gallons. All right, so once we know that X is representing the amount of bubbleberry fruit punch used in gallons. What else do we need? Well, we already know the amount of cherry smash. It tells us that in the problem. It tells us that she has 2 gallons of cherry smash. Okay, so let's go down to a little table and organize this information. So for our table, up here we're going to put the gallons. So this is going to be the gallons. This is going to be our concentration percentage as a decimal. And this amount right here is going to be our pure fruit juice. Okay. Then for our products over here, we're going to have the cherry smash and we're going to have the bubble berry. Okay. So those 2 products. Now it tells us in the problem the number of gallons of the cherry smash is going to be 2. And then we said the number of gallons of bubble berry that we're going to use is going to be represented with our variable x. What is the percentage of pure fruit juice in cherry smash? So let's go back up. So cherry smash, it tells us, is 50% pure fruit juice. 50% pure fruit juice. Whereas bubble berry is 14% pure fruit juice. Okay, so let's fill this part in. So cherry smash, again, is 50% fruit juice. So as a decimal, that's 0.5, okay? Bubble berry is 14% pure fruit juice. So as a decimal, that's 0.14. Now, as we just saw in our simple example a minute ago, all we need to do to get the amount of pure fruit juice here is multiply across. So for cherry smash, if I have 2 gallons of my fruit punch and it's 50% pure fruit juice, the amount of pure fruit juice in gallons there is going to be 2 times 0.5 or 1. Okay. Then for the bubble berry, I just got to multiply across again. So I have X gallons, it's 0.14 or 14% pure fruit juice. So the amount of pure fruit juice there is 0.14 times X. Okay. And again, this is in gallons. Now, we have this final row here that represents our mixture, our desired mixture. So we'll say this is our final mixture, okay? So the number of gallons will be what? Well, we only have gallons coming from 2 sources, right? We have the cherry smash and the bubble berry. So I can just add these. I would have X gallons coming from the bubble berry, then plus 2 gallons coming from the cherry smash. Now the percentage is given to us in the problem. It tells us that the final mixture, again, is 22% pure fruit juice. So this has to be 0.22. And so the pure fruit juice in gallons would be what? It would be 0.22 times this quantity of X plus 2. All right, so let's stop here. From this point, it's very easy to set up an equation. We know that the amount of pure fruit juice in gallons in the final mixture comes from 2 sources. It comes from this source right here. You've got 1 gallon coming from your cherry smash, and then you've got 0.14x gallons coming from your bubble berry. That has to be equal to the pure fruit juice in gallons in the final mixture. This 0.22 times the quantity X plus 2. So that's where we're going to get our equation. We're just going to set this up. So we will have 1, again, the amount of pure fruit juice in gallons from cherry smash, plus you're going to have your 0.14x, which again is the amount of gallons of pure fruit juice in the bubble berry. And we're going to set this equal to the amount of pure fruit juice in the final mixture, which is 0.22 times the quantity X plus 2. Okay, so once we've set up an equation, it's very easy. So you have your 1 plus 0.14x is equal to, use our distributive property, we'll have 0.22x, and then plus 2 times 0.22 is 0.44. And then to solve this guy, I'm just going to go ahead and subtract 0.14x away from each side of the equation. And I'm going to subtract 0.44 away from each side of the equation. And what's that going to give me? So we know that this would cancel. We know that this would cancel. So 1 minus 0.44 is 0.56. So the left side is 0.56. And this is equal to 0.22 minus 0.14 is 0.08. And then times x. If we finish this up by dividing both sides by 0.08, we're going to get 7. Okay? So x here is going to be equal to 7. Now, let's make sense of this. We said that x was the amount of bubble berry fruit punch used in gallons. So we know that x is equal to 7. So she needs to use 7 gallons of bubble berry fruit punch. Okay? So let's go back up and let's answer our question now. So we'll just say that she needs to use 7 gallons of bubbleberry fruit punch. Now, let's check this. Let's make sure the answer is reasonable. She's throwing a party and wants to serve fruit punch, which again is 22% pure fruit juice. She currently has 2 gallons of cherry smash fruit punch, which is 50% pure fruit juice. And again, it asks how many gallons of bubbleberry fruit juice, which is 14% pure fruit juice, must be added to create her desired fruit punch. Well, we know if she's using 7 gallons of bubbleberry fruit punch, and it's 14% pure fruit juice, then essentially she's getting 0.98 gallons of pure fruit juice from the bubbleberry. So this comes from the bubbleberry. Now, we're told, again, in the problem directly, that she's using 2 gallons of the cherry smash, and it's 50% pure fruit juice. So 2 gallons times 0.5 is again 1. So add that to 1. This is from the cherry smash. So this amount should be equal, this 1 plus 0.98, which is 1.98, should be equal to the amount of pure fruit juice in the final mixture. So in the final mixture, she's going to have 7 gallons of bubbleberry plus 2 gallons of cherry smash. So that's 9 gallons. And again, it's 22% pure fruit juice. And 9 times 0.22 is 1.98. So we're good to go, right? This is your final mixture. You basically have said that the amount of pure fruit juice coming from the bubbleberry and the cherry smash is equal to the amount of pure fruit juice in the final mixture, and it is 22% pure fruit juice, so we're good to go. She needs to use 7 gallons of bubbleberry fruit punch to make her desired fruit punch mixture. All right, let's take a look at another one. So Double Yield Farmers Market sells 24-ounce bags of mixed nuts that contain 43% peanuts. To make this product, they combine Rowlet mixed nuts, which contain 30% peanuts, and True Nut mixed nuts, which contain 50% peanuts. How much of each should be used to make their product? So again, another straightforward kind of question. How much of each? So we're saying how much of the Rowlet mixed nuts and how much of the True Nut mixed nuts should be used to make their product, which again is a 24-ounce bag of mixed nuts that contains 43% peanuts. Okay. So in this case, we don't know an amount for either, right? So we have to kind of get that. We're working with ounces. So the total amount in the final mixture that they sell is 24 ounces. So let's use that information to create a variable. So let's let x be equal to the amount in ounces of, we'll just go ahead and say Rowlet mixed nuts used, okay? Now, because the total mixture in the end is 24 ounces, we know that if we subtract away x, again, the amount in ounces of Rowlet mixed nuts used, what's going to happen is 24 minus x can represent the amount of the True Nut mixed nuts that's going to be used, right? So if we put then, we'll say 24, again, the total amount of ounces of the final mixture, minus x, which is the amount in ounces of Rowlet mixed nuts used. So this is going to be equal to the amount in ounces of the True Nut mixed nuts used, okay? So once we've kind of modeled this, we can go down to the little table and set things up, just like we did in the last example. So on the left, let me put the names. So you have your Rowlet, you have your Rowlet mixed nuts, you have your True Nut, and we're going to have a final product. So we'll have a final, you could say final mixture or final product. Okay, let me make that a little better. So again, final mixture. So up here we'll have our ounces of mixed nuts. And then we're going to have our concentration percentage of peanuts. So this is the percentage as the decimal. And then we're going to have pure peanuts in ounces. So this is pure peanuts. And again, this is in ounces because we're working with ounces. All right, for the ounces of mixed nuts, we know for Rowlet, we represented this with X. And for True Nut, we represented this with 24 minus X. For the final mixture, we know it's 24. Okay, that's given to us in the problem. Now the percentages, let's go back up. We're told that the final mixture is 43%. So this would be 43% or 0.43 as a decimal. Then we're told that Rowlet mixed nuts has 30% peanuts and True Nut has 50% peanuts. So let's go back down. So Rowlet is 30%, so 0.3 as a decimal. True Nut is 50%, so 0.5 as a decimal. And again, to get the amount of pure peanuts, we just multiply across. If it's 30% peanuts and it's X number of ounces, the ounces of pure peanuts would be 0.3 times X. Again, if it's 50% peanuts and there's 24 minus X ounces, the pure peanuts would be 0.5 times the quantity 24 minus X. And then for the final mixture, if it's 43% peanuts and there's 24 ounces of mixed nuts, well, I can multiply 0.43 times 24 to give me 10.32. This is the amount in ounces of pure peanuts in the final mixture. Now again, we can set up an equation in the same way that we did in the last problem. We basically think about the fact that the amount of pure peanuts coming from the Rowlet mixed nuts plus the amount of pure peanuts coming from the True Nut mixed nuts has to be equal to the amount of pure peanuts in the final mixture. So all I've got to do is take this 0.3x and add it to my 0.5 times the quantity 24 minus x, and then set this equal to my 10.32. So let's solve this and we'll be good to go. So we have our 0.3x plus 0.5 times 24 is 12. Then minus, you have 0.5 times x, which is 0.5x. This equals 10.32. 0.3x minus 0.5x is going to give us a negative 0.2x. Then you have your plus 12 equals 10.32. Let's go ahead and subtract 12 away from each side of the equation. And this is going to cancel. You have your negative 0.2x is equal to, if I do 10.32 minus 12, I get negative 1.68. So negative 1.68. As a final step, let's divide both sides by negative 0.2. And then this cancels with this. We'll have that, let me kind of make a border here. We'll have that x is equal to negative 1.68 divided by negative 0.2 is going to be 8.4. Okay, so 8.4. So let's go back up. So this is going to be 8.4. And then 24 minus 8.4, or 15.6, is going to be the amount in ounces of True Nut mixed nuts used. So let's go back up. We'll make a nice little sentence here. We'll say that they should use 8.4 ounces of Rowlet make that better. Again, mixed nuts. And you have 15.6 ounces of True Nut mixed nuts. So True Nut mixed nuts. Okay. So again, they should use 8.4 ounces of Rowlet mixed nuts and 15.6 ounces of True Nut mixed nuts. All right, so to check this, the first thing you want to do is make sure that the number of ounces coming from Rowlet mixed nuts and the number of ounces coming from the True Nut mixed nuts match up. So you've got 8.4 ounces coming from Rowlet mixed nuts and 15.6 ounces coming from the True Nut mixed nuts. That does give you 24 ounces, okay? 15.6 plus 8.4 would give you 24. So you're good to go there. If, again, we have a 24-ounce bag that's 43% peanuts, we know there's 10.32 ounces of pure peanuts in that product. Now, this comes from what? It comes from the Rowlet mixed nuts, which is 30% peanuts. So 8.4 times 0.3 is going to give us 2.52. And then it also comes from 15.6 ounces of True Nut mixed nuts, which is 50% peanuts. So 15.6 times 0.5 is 7.8. So if you take the 7.8, the amount of pure peanuts coming from True Nut mixed nuts, and you add that to the 2.52, again, the number of ounces of pure peanuts from the Rowlet mixed nuts, you do get your 10.32, or again, the number of ounces of pure peanuts in your final product for the double yield farmers market. So we can say our answer here is correct. Again, they should use 8.4 ounces of Rowlett mixed nuts and 15.6 ounces of True Nut mixed nuts. All right, let's take a look at one more of these. So Jacob wants to make 17.5 gallons of a 44% acid solution. To do this, he will mix a 60% acid solution and a 25% acid solution. How much of each solution must he use? Again, very simple problem. The key to understanding this here, again, is to think about the final mixture. It's 17.5 gallons of a 44% acid solution. So basically we have 17.5 gallons, 44% of it is pure acid. Now, this can only come from what? Two sources here. We've got a certain number of gallons, which is unknown at this point, of a 60% acid solution, and then a certain number of gallons, again, unknown at this point, of a 25% acid solution. Now, if we let a variable like x be equal to the amount in gallons of the 60% acid solution that we're going to use, then what can we say about the amount of the 25% acid solution we're going to use? Again, the total amount in gallons is 17.5. So we could say then 17.5. Again, the total amount in gallons of the final solution minus x. Again, the amount in gallons of the 60% acid solution we're going to use. This is going to be equal to the amount in gallons of the 25% acid solution and let me just drag this to another page so it's nice and clean. So let's go down to a little table real quick and let's kind of set this up. So we know that we want to have gallons of the acid solution. So this is gallons right here. We know we want a percentage concentration basically of acid. And then we're going to have the amount of pure acid. Okay, and of course this is going to be in gallons. Now we have our 60% acid solution. We have our 25% acid solution. And then we have our final mixture. Okay, so the number of gallons for the final mixture is given to us as 17.5 in the problem. We assigned our variable x to represent the amount of gallons for the 60% acid solution. Let me make that clear because that looks like 66. And then we said that 17.5, again, the amount in gallons of the final mixture, minus x, the amount of gallons for the 60% acid solution that we're using, is going to be the amount of the 25% acid solution that we're going to use, okay? So we have the number of gallons modeled for each. The percentage is very easy because it's off to the left, right? So this one right here is going to be 0.6 as a decimal, right? That's 60%. And this one right here would be 0.25 as a decimal. That's 25%. So the final mixture, we are told, is 44%. Again, Jacob wants to make 17.5 gallons of a 44% acid solution. So as a decimal, 44% is 0.44. So to get the amount of pure acid in gallons for each, I would just multiply across. So I have x gallons and it's 60% pure acid. So 0.6 times x is 0.6x. I have 17.5 minus x gallons. It's 25% pure acid. So 0.25 times the quantity, 17.5 minus x. And then my final mixture is 44% acid and it's 17.5 gallons. If we multiply those together, you get 7.7. So this is the amount of pure acid in the final mixture. It's 7.7 gallons. Now, for our equation, again, we use a similar format. We think about the amount of pure acid coming from the 60% acid solution, which is 0.6x, plus the amount of pure acid coming from the 25% acid solution, which is 0.25, times the quantity 17.5 minus x. And this has to be equal to the amount of pure acid in the final mixture, right? So 7.7. Okay, so let's solve this equation and we'll be good to go. So we have that 0.6x plus 0.25 times 17.5 is 4.375. And then minus 0.25 times x is 0.25x. And this equals 7.7. Okay, So let's clean up on the left. 0.6x minus 0.25x is 0.35x. So 0.35x, and then if I subtract 4.375 away from each side, what will I get? Well, we know this would cancel, so we'll say this is equal to 7.7 minus 4.375 is 3.325. All right, so to finish this up, let's divide both sides of the equation by 0.35. So we'll get x is equal to 9.5. Okay, so let's go back up. So again, we said that x was the amount in gallons of the 60% acid solution. So this is going to be 9.5. And then 17.5 minus 9.5 is going to give me 8. So there's 8 gallons of the 25% acid that's used. So let's go back up. And to answer this, we'll say he should use 9.5 gallons of the 60% acid solution, along with 8 gallons of the 25% acid solution. Again, very easy to check. First, you would say, is 9.5 plus 8, the gallons coming from each source, if you add those together, is that 17.5, right? The number of gallons in the final mixture that he has. Well, yes, it is, right? 9.5 plus 8 is 17.5, so that part checks out. All right, now next, remember, he has 7.7 gallons of pure acid in the final solution. That came from multiplying 17.5, the number of gallons in the final mixture, times 0.44, again, 44% as a decimal. That gives us 7.7 gallons of pure acid in the final mixture. So that comes from two sources. From one source, he has 9.5 gallons, that's 60% acid. So that would be 5.7 gallons of pure acid. Then lastly, he has 8 gallons, that's 25% acid. So 8 times 0.25 is 2. So if you add 2 to 5.7, you do get 7.7. Right, so you've checked the amount of pure acid in the final mixture, that matches up. And you've checked the number of gallons of the final mixture, that matches up. So we can say our solution here is correct. He should use 9.5 gallons of the 60% acid solution, along with 8 gallons of the 25% acid solution.